In 1895, if I'm not mistaken, an Italian inventor called Marconi showed us how to communicate using radios. So he was credited to inventing the first radio. So after 100 years, it's not as difficult as that it was before 100 years to make a radio or even some other electronic component, electronic device. So for example, if you take the radio, we know what is expected from a radio. So it should get some signals, the radio signals, and then we should somehow process the signals inside the radio, and then we should somehow get the sound we want from the channel out of the speakers. So since we know what exactly that goes on inside, and also we know a lot about these electronic components that's out there, like transistors, capacitors, resistors. Also, if you think of digital electronics, the ICs, the small chips you have, we know how they behave quite well, very well. And we know how, when we put them together, we know what behavior we can expect. So since we know what behavior we want in the radio, and since we know about the components and how they behave, we can put them together inside the radio so that it behaves as what we desire. It behaves as a radio. So a few years ago, maybe even before, people started thinking, can we do this in biology? Can we look at biological components as the components in electronics? Can we put things together using these biological components so that they behave as we want, as the things that are not existent in nature? So in summer 2010, I was in a team of students, of 8 students, for computer science people, for biology people, and it was for a competition in synthetic biology. So this field is referred to as synthetic biology. We actually designed a bacterium that can be whose motion can be controlled using light. So usually there is this bacterium that shows some random motion, which is referred to as chemotaxis. And this is usually based on the concentration of food inside the media it is moving. So it's not very directed. It's only deciding how it tumbles. So if it decides only if it tumbles or goes straight. And we actually manipulated, okay, it's not a nice word. So we introduced new components into this cell so that we could give light signals that can change if it goes straight, or if it tumbles. So this was a success, and we presented this in IGM competition in 2010 in MIT, and actually we won a prize also. So, however, a point I would like to say is that, so imagine writing a software program. If there's something wrong, we can freeze the program and observe individual states as they are very easily using a debugger. It's very easy to fix them. And when it comes to computer science from electronics, it's a bit more difficult because we are working with physical components. We cannot really freeze everything, but we can, of course, observe the states using oscilloscopes and stuff like this. But when it comes to biology, the measurements are very indirect. You cannot really freeze the system. So the complexities are much higher, the challenges are much higher, but of course the rewards are much, much higher. Thanks.